Now I introduce prioritize the experience replay. When we use sequential samples or episodic samples to train a reinforcement learning model, we have two issues. First one is a correlation between the sequential samples because it violates the ID requirement of the input data by using the stochastic gradient descent method. Second, we use the samples only one time and throw it away. It's not data efficient. To solve these two issues, experience replay splits the sequential sampling or episodic sampling into one-step experience and put the one-step experience into a replay buffer. One step experience is a for tuple, includes this current state, action taken at the current state, move from a current state to the next state and receive reward R. When we use this data to train the reinforcement learning, the experience replay just picks samples from here without considering the importance of the samples to train the reinforcement learning model. Use this way, the samples in the replay buffer is with less correlation, and we can reuse the data. We will have a higher data efficiency. However, experience replay just picks a sample or pick the experience from the replay buffer without considering the importance of the samples. It's not a good idea because each experience have different importance and will affect the model training. That's why here we will introduce advanced replay method is called prioritize the experience replay. To label the importance of the samples in the replay buffer, we have, we need to have a criterion. Let's just think about, when we use the gradient descent method to train a Q learning model, we need to first define objective function, and then we calculate gradient of the objective function, and use that gradient to update the model parameters theta, let's see. We know the gradient of the objective function is proportional to the TD arrow theta. This is theta equal to 2 parts. This is the target, and this is the current Q value function address DS, and this action A. That means, this TD arrow is a good one for the to label the importance of the samples in the replay buffer. That means if transition with the higher TD arrow, you will have more contribution to the gradient of the object function and help faster find the optimal policy. So once, the good thing is when we use this Q-learning to train the model, every iteration, we already have this time difference error. So we can use this arrow, add this arrow as the one more index into the samples in the replay buffer. So that means each time we just scan all the transitions and find the transition with the maximum TD error and use that transition to update the model and get a faster convergence performance. However, if we use this greedy experience and replay, we need every iteration, we need to scan the transitions and find the maximum transition. That's transition with the maximum TD error data. That's not, this time confusion. That's why we can introduce the second advanced experience replay method. It's called stochastic prioritization. That means, this method is between greedy method and the uniform method. We define priority for each samples in the replay buffer. Then we use this one define the normalized probability of the sampling transition. So use this formulation. We consider two cases. One is we call proportional prioritization. That means we assign this TD arrow theta as the priority of the transition I. We plus this, we add this small number to make sure even this TD arrow is equal to 0, the transition still have a chance to be visited. And the second is ranked based method. That means we define this priority for each transition I as this rank from this rank. This rank then means if a transition is visited frequently, and then its priority will be reduced. That means we encourage the method to explore, to find the transition with a less rank. Here we show the comparison between different methods. This one is called oracle. Oracle is the ideal case. That means actually state. You find all the possible next state, see which one can generate a less global loss. Of course, that's an ideal case. So this is the best. And this is a greedy method. And this is the uniform. You can see the greedy method is better than the uniform. And here we have two cases. One is the proportional, and one is the rank-based cases, the method. So they are almost the same, and both are better than the uniform. And here we also put the oracle case here. For more details, please check with this reference. Thank you.